Hello and welcome to day 4 of learning ML from chatgpt. So yesterday we learned about tensors and with both TensorFlow and PyTorch, how to create tensors, reshape them, index them, and slice them. So please give me day 4's lesson on ML. I'll just paste in day 4. Linear regression with TensorFlow and PyTorch. Can we just do this at the start though? We'll probably give more in-depth explanation there, so it'll be fine. Day 4, linear regression with TensorFlow and PyTorch. Today you'll learn how to implement a simple linear regression model using TensorFlow and PyTorch. Linear regression is a fundamental machine learning algorithm that models the relationship between a dependent variable and one or more independent variables. By the end of the day, you'll be able to create, train, and evaluate a linear regression model in both frameworks. So, linear regression with deep learning frameworks. Linear regression, a method to model the relationship between a dependent variable output and one or more independent variables inputs. The model assumes a linear relationship between inputs and the output. Deep learning frameworks like TensorFlow and PyTorch provide high-level abstractions that make implementing linear regression straightforward. These frameworks handle the heavy lifting of matrix operations, gradient computations, and optimizations. For a simple linear regression with one feature, prediction equals weight times feature plus bias. So we'll learn what these mean, I think. Yeah. If not, I'll ask it to explain it. So part 1, linear regression with TensorFlow. First, let's start by preparing our environment and data. So here we're just making a random data set like we did in the first lesson, I think it was. And then we're creating a TensorFlow tensor with X. So so these are our data sets, and we're just converting these to TensorFlow tensors. Then we define the linear regression model using Keras layers dense, which is a fully connected layer. Sequential, okay. Units 1, input shape 1. Model.compile optimizer. What's SGD? So loss is mean squared error, okay. That's what I would use, as it punishes like huge ones that vary above or below the line in which the gradient descends the sides. Now we'll train the model. So model.fit epoch verbose. So will it actually explain it? It's not really explaining it. I'm going to just ask it again. Please give a lot of detail about the technical concepts and words used. That should be it. Like explaining bias, weight, feature, and feature. Please also explain what each line does. Okay, this should give a better explanation. So, just talking about what we're doing, predict house prices. Linear regression, mathematical representation. So, linear regression projects formula y input feature, weight determines the slope, okay, and its learnable parameter in the model. Bias, which adjusts the line to better fit by shifting up or down, it's also a learnable parameter. Okay, so adjust the line. So I assume this is in the gradient descent algorithm, where or is it now? Which adjusts the line to better fit the data by shifting it up or down. So is that when in the gradient descent, when we're training it for that specific like gradient of the line, that's how much we move it up and down in order to, like, because the bias doesn't need to be too big or too small. It needs to have like an equilibrium between those two predicted values. So when there are multiple features, so a feature is a variable used as an input to the model. For example, in house prediction, features simply is weight, a coefficient assigned to the feature. The model learns the optimal weight during training, adjusting it to minimize the difference between predicted and actual values. Bias, a term added to the prediction. The bias allows the model to fit data even if the relationship between features and target isn't centered around the origin. Loss function, a function that measures how well the model's predictions match the actual target's values. For linear regression, we typically use mean squared error, which calculates the average of squared differences between predicted and actual values. I don't understand this equation, but I'm pretty sure this is sum of 1 over n, sum of n, then you increment by 1, is it? To be honest, I don't know. Where y1 is the actual value, y1 with a hat is predicted value. Oh, okay, so this is we're just squaring the difference, and then we're summing it all, and then we're taking the mean. Okay, not too complicated. So an optimizer, an algorithm that adjusts the weights and bias to minimize the loss function. A common optimizer is stochastic gradient descent. So part 1, linear regression. So we were setting this up. So generates. Okay, so we got to this bit, which was all fine. In TensorFlow, we use tf.keras.sequential to define a model. A linear regression model can be implemented with a single dense, fully connected layer. Okay. So we just need to know whether it's dense or like sparse on a specific problem. So specifically with gradient descent, we know it's dense. And we can compile the model, optimizer, use add a layer, a dense layer with one output unit because it's a single. Okay. One output unit. What was it saying? A single layer with one unit. Oh yeah, because it's only a one layer. Configures the model for training. The optimizer assumes you will update the weights and bias to minimize. Okay. That's pretty easy actually. So we train the model using the fit method, which iterates over the data to learn weights and bias. Trains the model for 100 iterations, epochs. Each epoch updates the weights and bias slightly to reduce. Okay. So epochs are just how many iterations we'll do. Like the more epochs, I guess it means it will take longer, but the model will be more precise. So then we can evaluate the model. After training, we can evaluate the model by making predictions and examining the parameters. So weights, biases, model.layers at 0 because we've only got one layer there, and then we get the weights. Okay, model predict. We choose to learn weight and bias from the model's first and only layer. So this is the X. Wait. Oh yeah, we're predicting the Y. Wait, are we? We're passing in Y here. So this is just pre-trained. So if we added some extra data, it would be able to train it on this. And then we can check whether the X, what we predict with X to be the same as Y. So now we move on to PyTorch. Now let's implement the same linear regression model using PyTorch, another popular deep learning framework. We will start by importing the necessary libraries and preparing the data similar to TensorFlow. Import PyTorch, import neural network, import optimization model. So x equals torch.tensor. So convert numpy array to, okay. So we're just using the code that we got up here, and there's some built-in function to convert from NumPy to PyTorch tensor. So I assume this is just float. So last video we were getting errors with because they were of different data types, so it was hard to resize and add different tensors. Define the linear regression model. So we're making a class here. Looks like we're inheriting from neural network module. Yeah, a subclass of neural network module. So super calls the parents class constructor. Linear regression model self in it, and then self.linear. Create a linear layer with one input and one output. Okay, and forward, define the forward class, how data flows through the model. It will explain it here. So base class for all neural network modules in PyTorch. Define a linear layer with one input feature and one output, single output regression. And then forward defines how the data moves through the model, i.e. from input to output. Then define the loss function and optimizer. So we're going to use MSE loss, and then SGD is the same one we used above. Train the model. So we're going for 100 epochs, and we're going to train the model. So it looks a bit more verbose than TensorFlow, but it still works. Predictions equals model X, loss equals criterion, 0 grad, loss backward. Okay. Do we need to learn this? Because it's a bit complex, but surely. Anyway. Loss backward, optimizer step. So for every 10 epochs, we're going to print what the loss is. And that will show us that as the model keeps going through all of the optimizations, the loss will be less. Evaluate the model. So for name, param, learned weight, and learned bias. Okay. Assignment. Use the TensorFlow and PyTorch framework to build a linear regression that predicts that. Okay. So load the data, preprocess it to obtain input features. Let me just click on this. How do I? I'll look it up. California. California housing prices. Kaggle. Okay. So let's download this. Okay. Oh, I'm gonna need to just log in for a minute as I need to create an account in order to get this data set. Okay. If my Google works, we should be able to do this soon. Oh, it's taking a while. There's a lot of okay, nearly completed. So if I now download, this should work. Okay, now I'm just going to unzip the file. And extract tool. So now we have the housing.csv file. I'm going to drag this into here. How do I add a file? I'm just trying to add the file into the Google Colab. Is it here? Okay, I'm just gonna have to troubleshoot this. So downloads, archive CSV file, housing CSV file. Wait, I'll put it on the screen. You can see I'm trying to input this, but sadly it's not. Oh. Do we have a file? Okay. What I'm going to do instead is I'm just going to... I like the TensorFlow one here more, as it's much more concise. So, what I'm going to do... I'm just going to go to the TensorFlow one and see if this works. Okay, so you need to import TensorFlow. Here we're just preparing the dataset. We can think of this as just the housing prices dataset. And then we create a TF-Keras sequential model with a dense layer, only one dense layer, which is what you need for linear regression. And then we fit the model with 100 epochs, which is how many iterations we'll go through. And then there's the predictions. And we'll see if this works. So we print learned weight and learned bias. So now we have got Gemini, as we are working with Gemini. Generate. Now, please write some code to use matplotlib to print this model. Print this linear regression model visualization. It's not very good. Oh, can't do it. Let's see. Okay, it looks like Gemini can't use it in a minute. So now for the PyTorch, no, for the TensorFlow linear regression example, please provide the code which would visualize this linear regression. Oh, it's just refining the full code now. So wait for this to finish. So just to recap, having the sequential model with a dense layer, units 1 as we're going, input is 1, the shape of 1, and output shape of 1. So then we're compiling it with the SGD optimizer, which is just like how we optimize it to get the bias and the weights, and then the mean squared error is what we want to minimize in order to have a better model. So I'm just going to paste this in to here and see if this works. As there are 100 epochs, it might take a while. Like the last one took quite a while. 10 seconds. 12 seconds. Okay, whoa. So we can see for some reason our line is not optimal. Maybe if we increase the amount of epochs to 200, we'll see if this will work better. It'll fit. As you can see, the more epochs we have here, the better the line is getting. Because we're having more iterations, so we can. And are we passing any specific bias here? Verbose 0. Okay. So verbose, I think, just it doesn't print out all the steps that it's doing. And this with 400, which is quadruple the amount we had originally. Yeah. It's still not exact, but if I increase this now to 800, but the thing is with linear regression, you've got to have a suitable trade-off with the amount of epochs, like the time complexity, and also the rate. So you don't want to have it like super quick, but then like the line has no correlation with the actual data. Like you want to have the equilibrium, as I mentioned earlier. Okay. As you can see, this line is almost perfect. It's going right through the middle, and yeah. So here it looks like suitable, or we could have changed the I can't remember I think it was bias maybe. The amount of time, that's the number that you change the line. However much you change the the bias is the, like when you have y equals mx plus c, m is the weight, and or c is the like what's it weight, and there's bias. Yeah, I think that's, but I'm not 100% sure. But as you can see, this line, it performs the job and it's very effective now. But this is like 8 times the original amount of epochs that we had. So that will conclude our day 4 of learning ML from chatgpt. So thank you for watching, and I'll see you in the next video. Goodbye.